Okay, so in this video we will solve a problem on collision, and the problem has got certain special features or special characteristics that will help us get a somewhat more better resolution into some of the intricacies of solving problems involving collisions. So the problem goes as follows. So here we have an inclined plane, okay, and this inclined plane is resting on a horizontal surface, and there is a particle that falls vertically and hits the this inclined plane with a velocity of v0. Okay, now the particle is of mass m and the incline is of mass 2m. Okay, now the incline is free to slide on the horizontal surface without any friction. Alright, now the coefficient of restitution of this collision is E between this particle and the incline. Okay, so the idea is that the ball is or the particle is going to collide with this inclined plane, and as you can intuitively see, by the way, the inclined plane is an angle theta, sorry, and so the particle is going to collide with this inclined plane and then rebound in a certain direction, and the inclined plane is going to move in the horizontal direction because that is the only direction it is allowed to move in. And so the goal is to find the velocities. So determine the velocities of let me just determine the velocities of particle and incline after impact. So this is the problem. Now typically when we solve problems in involving impacts, as you may know, what we do is we use two sets of concepts. One is the conservation of, in this case, because it's there is no rotation involved, conservation of linear momentum, and the other set of concepts that we use is that of coefficient of restitution. So we'll delve into those in somewhat more detail in solving this problem, and we'll try to highlight the peculiarities of this problem and how to deal with those peculiarities in terms of formulating the equations, the conservation equations and the coefficient of restitution equations. Alright, so in problems like this, to do a deep dive and get a better understanding of the interactions that occur that lead to the resulting velocities, it is probably a good idea to to show the impulsive forces that are generated at the point of impact. So if we consider the incline, now let us consider this the condition, or let us consider the forces or the impulsive forces that are acting right at the instant of collision. So you can see that at the instant of collision, the ball or the particle collides with this surface. So therefore it produces an impulse. Let's call it F delta t, where F is that force and delta t is that infinitesimally small duration over which that force acts. And so this is the impulse. F delta t is the impulse. Now when that happens simultaneously, because the incline is in contact with the ground, the incline also applies an impulse on the ground, and the ground applies an equal and opposite impulse, and let's call that F bar delta t. Okay, we do not know what is the magnitude of that force F bar, and hence we keep the impulse as F bar delta t. Now in addition to this, if we consider the presence of gravity, although the presence of gravity will, as we will see, will not affect the results that we will arrive at, but just for the sake of completeness, what we should be doing in identifying the impulses is to identify all the forces that are acting on this incline at the instant of the impact, and then show or formulate the impulses due to those forces. And if we do so, then it makes sense to also include the impulse due to gravitational force. So it will have a 2 mg and a delta t. So that delta t is the infinitesimally small duration over which the collision happens. So delta t is the infinitesimally small duration over which collision occurs. All right. Now we know that as a effect of these impulses, what's going to happen is that this incline is going to have a motion, and because it is not allowed to go in the vertical direction because of the ground, the only direction that it can travel is in the horizontal direction, and we will call the inclined object 2, and we will call the velocity that is generated due to the collision as v2x. Okay, and for that matter we will also designate the horizontal direction as I, or that will be the unit vector along the horizontal direction, and j is going to be the unit vector in the j direction. You could say that the horizontal direction is x and the vertical direction is y. Okay, so this is then the impulse diagram of the inclined plane. Now similarly we can have an impulse diagram of the particle itself. So when the particle collides, and this is this infinitesimally small duration over which the collision happens. So when the collision happens, there is going to be an equal and opposite impulse that is exchanged between the particle and the incline. So the particle is going to experience f delta t, and this angle is theta. So you can see that let's see. Yeah, so this angle is also theta. Okay, and for the sake of completeness, we can also say that there is going to be an impulse due to the gravitational force during that small duration, and it's going to be directed downwards, right? So there are two impulses. So this will make sure that we have covered all the forces and the associated impulses during the collision. So this is our object 1, and this is of mass m. So now we can if we stick to the basics, then what we can do is we can formulate this problem from the basic principles of impulse momentum equations. So the basic linear impulse momentum equation says, oh, by the way, I should mention that after the collision happens, we don't know in what direction the particle is going to move. So we are going to say that there is a v1x, a velocity in the x direction that's going to be generated after impact, and a velocity v1y that is going to be generated also after impact, understanding that before the impact there is a v0. So v1y is the velocity of the particle after the impact, v1x is the velocity of the particle in the x direction after impact. We have, without any assumption, we have given the directions of the velocity components after the impact to be along the positive x and positive y. Okay, so that's the general direction. For the velocity before impact, we already know that it is going downwards, so it is in the negative y direction. So that is the setup. So let us now take the approach of writing the impulse momentum equations. So impulse momentum equations. The impulse momentum equations for a particle or even for a rigid body. For a rigid body, the impulse momentum equations are both in the linear as well as in the rotational sense. But for particles, and here we are not considering the dimensions of this because there is no rotation involved of the incline. So we are only limited to linear impulse momentum equations. And the linear impulse momentum equations are quite simple. They basically say that the change in velocity, or the change in momentum rather, of a particle along a certain direction is due to the net impulse along that direction. So then for the particle 2 along the x-axis, we can say that, now note that f delta t is making an angle theta with the vertical. So we can say that f delta t sine theta is equal to the change in momentum of the incline in the x direction. So that is 2m v2x minus 0 is equal to 2m v2x, right? So let's say this is our first equation. So it's quite simple. It says that the net impulse in the x direction equals the change in momentum for the incline in the x direction. Now same for 2 along y, we will have there is no motion. Note that in the y direction there is no motion, so all these impulses must cancel each other. So then we have f delta t cosine theta plus 2mg delta t is equal to f bar delta t. So this forms our equation 2. So note that equation 2 really does not relate any momentum, it just relates the impulses along the y direction. And that is because there is no velocity of this incline along the vertical direction, because there is just the ground. Now you could similarly now write an impulse momentum, you could similarly show an impulse for the ground and say that the ground experiences an impulse f bar delta t. Now if you were to write an impulse momentum equation for the ground, we have a problem, because the ground is not moving because it has got an infinite amount of inertia. So that's the assumption. We are assuming that the ground has infinite amount of inertia. So how do we say that how do we write f hat delta t equals some change in momentum? That is not possible because the ground has infinite amount of inertia. So then it begs the question that does it mean that f bar of delta t is equal to 0? And the answer is no. F bar times delta t is a non-zero quantity. However, it is applying on a surface that has infinite inertia, and so all that impulse is just going to be absorbed by the inertia without change in any noticeable momentum. Okay, and so the idea is, if I write impulse momentum equation for the ground, I don't get any useful equation. Okay, so this is one of the peculiarities of this problem, where you have the direction of the ground where there is an infinite inertia. It is not allowing motion in that direction, and hence what is happening is that when you write the impulse momentum equations, the impulses show up, but the momentum does not show up. Okay, so so we need to be cognizant of these scenarios, and accordingly be able to formulate our impulse momentum equations correctly, and ultimately we should be able to have a correct formulation of the conservation of momentum equation, which we are going to get to shortly. Now for one, which is this particle, we have along x, we can say that now the impulse along the x direction is f delta t cosine theta, but with a negative sign, because we are considering x to be positive in the going from left to right. So we will have, let me just check here, yeah, so we will have negative f delta t sine theta to be equal to the change in momentum in the x direction for particle 1. So m v1x minus 0 is equal to m v1x. So that's equation 3. Alright, and similarly for 1 along y, we will have f delta t cosine theta minus mg delta t is equal to the net change in momentum in the y direction, so that is mv1y minus the original momentum in the y direction, which is minus mv0. Note that the initial momentum along the y direction is minus mv0 because v0 is downwards. So essentially what we have is that f delta t cosine theta minus mg delta t is equal to mv1y plus mv0, and this becomes our equation 4. Okay. Now the idea of the conservation of linear momentum equations in these collision problems is that if you carefully look at these impulse momentum equations, then the idea is that you can combine a set of equations and eliminate these impulse expressions and come up with a relation between just the velocities of the different masses that are undergoing collision. When we are able to do that and we are able to derive an equation of that nature, then those equations become our conservation of linear momentum equations for the overall system. So again, the idea is that if we can combine two or more of these equations, and in such a way that the impulse terms get cancelled, and so all we get is the momentum expressions on both sides of the equation. That expression then serves as a momentum conservation equation for the overall system, okay, during the collision. So if we can do that, that's a momentum conservation equation. If we cannot, then it means that the momentum is not being conserved for the overall system. So now if you consider the equations 1 and 3, you will see that let me just make some space here. So adding equations 1 and 3, what we get is 2mvx as 2mv2x is equal to sorry, 2mv2x plus mv1x is equal to 0. So let me write it a little bit more clearly. 2mv2x plus mv1x is equal to 0, or in other words 2v2x is equal to minus v1x. This is a classic conservation of momentum equation, especially if you consider this. What we have done is we have eliminated this f dot sine theta term by adding equations 1 and 3, and what we are left with is just a conservation of momentum equation which is true during the collision. So this is now one thing to keep in mind is that this is telling us that momentum is conserved along the x direction. So therefore linear momentum is conserved along x direction. Now, in collision problems, we typically understand that linear momentum is conserved in any direction, which is true. The linear momentum is conserved in any direction. However, in scenarios like this, like this problem where we have one direction that is completely blocked off, that is the vertical direction in this case, it is blocked off. It is not allowing any motion of this block in this case, of this incline in this case, because of the infinite inertia coming from the ground. There, if we try to combine the momentum, the impulse momentum equations, what happens is that we cannot completely eliminate the impulses because we cannot formulate the momentum change for the infinite mass. So for instance, if I combine 2 and 4, you will see that there is a problem. So let me see. So you have 2 here, you have 4 here. So if I try to eliminate this f delta t cosine theta, what I would do is I would subtract, let's say, 4 from 2. So 2 minus 4 will give me 2 mg delta t plus mg delta t is equal to f bar delta t minus m v1y minus m v naught, or in other words, 3 mg delta t is equal to f bar delta t minus m v1y minus m v naught. And so equation 6 is problematic because I cannot use it. And the reason I cannot use it is first, you have this delta t term. We do not know what is this infinitesimal time instant. We also do not know what this f bar is, and there is no way for us to find out f bar because that is an impulse that is coming from the ground. Equal and opposite impulse is going to the ground, but since the ground has got infinite inertia, then we cannot formulate f bar t to be equal to a change in momentum. So therefore, one thing that we observe is that if there is a certain direction in which motion is disallowed or motion is blocked for the system of particles that are interacting in a collision, then along that direction the conservation of momentum equation does not give us any usable equation. So we'll make that point. We'll make the point in context of this problem specifically. We'll say that therefore in the scenario that motion is blocked along a certain direction, the conservation of momentum equation in that direction is not usable due to the presence of an effective infinite inertia in that direction. And you can say this is an inertia or infinite mass. Okay, so in context of this problem, what we see is that therefore the linear momentum equation can be only the linear momentum conservation equation can only be written along the direction where there is no restriction, and that direction is the horizontal direction. So in the context of this problem, the only direction where motion is not blocked is the x direction. Hence, linear momentum conservation can be formulated yielding a useful equation, a usable equation only in the x direction. Now you may be curious if I can write the linear momentum conservation equation about any other inclined direction, and the answer is no. As long as that inclined direction has a component in the vertical, along the vertical, then you are still encountering that infinite inertia, right? You are still encountering the direction where the motion is blocked. So the idea is, if I take any direction and that direction has got a component in the vertical direction in the context of this problem, or in general along the direction where motion is blocked, then that inclined direction will also not be and will also not yield a usable linear momentum conservation equation. So this is what we cover in this video. So we have shown in this problem how to write the linear impulse momentum equations, and from there how to derive the momentum conservation equation. The reason we took the linear impulse momentum equation is to show the problems that we have when motion is blocked in one direction. And so our analysis showed that the conservation of linear momentum equation can only be written in collision problems along the direction where there is no restriction, no blockage in the motion. So in the future videos, what we'll do is, now we will invoke the coefficient of restitution equation and other equations as needed and solve the problem and find the velocities immediately after the impact. So that's it.